Hey, Robert, do you ever want to give things to your children? Like when you die?
There's an interview question that I ask. It's the polymorphism one. I ask it all the time. It was the thing that I fell in love with.
Oh, yeah. Well, I mean, I think it's the most, well, I don't know about the exact question, but I think it's one of the quintessential, like, things that are always taught in school of, you know, hey, if you were to abstract a way of, you know, I want a list of things and they all need to be in the same list. Like, how do you do that? And polymorphism is the answer.
Yeah.
It's like, you know, if you want a duck and a dog and a cat, well, they're all inheriting from an animal.
Yep. And you can, they can share functionality. You can have abstract methods that can be unique across all of them.
Like, how do they walk?
Yeah, but you can interact with every animal and say walk, and it'll look at what type of subclass is this type of animal, and it'll call the child class's walk method.
Yeah.
It's a beautiful concept, and it was really the thing that made me fall in love with programming. But
somebody came along and just said, hey, what about a fish?
Yeah, what about a fish? Yeah, I mean, it's funny because a fish is an animal. Yeah, and then it's well, now I got to rethink everything. I got to recreate my base class, my parent class. I got to add a child, a grandchild, a nephew,
Well, that's where I think the difference is between the zoo and aquarium. So you got them separated already, so that's handled.
Yeah,
but for real though, right?
We laugh, but yeah, that problem is real. It happens in a lot of businesses, and it starts with trying to overuse inheritance. And there's a group of gentlemen who are known as the Gang of Four, who coined a phrase among many, favor composition over inheritance.
Yeah, and they they literally wrote a book called The Gang of Four.
Yeah.
So
yeah.
I mean, and really, I think this is big in the 90s, 2000s when, and I think just kind of putting a little perspective in the era here, like C, C++, that's really the heyday of those languages.
Yeah.
.NET was starting to become a thing. Client-side programming like JavaScript started to exist.
Object-oriented programming was
object-oriented programming was king.
It was hot, and
the only way to get things to reuse functionality was inheritance.
Yeah. Well, I think you had interfaces with C++. No?
No. They stole that from C# later in 2010s. Yeah, it's the same thing with pointers. C# you don't have to manage your pointers. Same thing with Java. C++, I think it was C++ 13 or something like that, stole the concept and they called them smart pointers. So it is a give and take in that way.
Yeah, but the idea of polymorphism being this beautiful way of creating this perfect architecture, where you've implemented a perfectly dry system where nothing is repeated. Everything's reused perfectly.
Mm-hmm.
It's
dry
almost,
being don't repeat yourself.
Yeah. But that isn't the world we live in. We live in a world where there's this constant evolution, this constant change,
mm-hmm.
and change is the enemy of good architecture. Let's talk about the problem. Well, let's define inheritance first. Let's go really basic, and let's talk about the problem that you get with it.
Yeah, so with inheritance, there's a couple different ways to look at it. And one of the quintessential ways that are definitely taught in school is vehicles. Right? You got a car, and then you've got a truck. Okay, so how do you get those things to be the same? Well, if you abstract them away, well, they're both vehicles.
Yep.
Okay, well, now let's add a van to it. Oh, easy. It's a vehicle. Let's add a motorcycle. Boom. It's a vehicle, right? So they all work.
And they're all different enough to where you're kind of okay with...
You're good with implementing a new class. Like you got a class of motorcycle because it's going to have two wheels. You can have a car because it's meant for passengers. So you can have 4 seats. You can have a truck. In a traditional sense, you're going to have 2 seats and it's meant for hauling. And a van is a big old thing that you're going to throw all your fishing gear in the back, maybe.
Yeah.
I don't know, but yeah.
And now we introduce the crossover.
Yeah, so like where do you put that?
Where do you put it? Because it's like it's a truck, it's a car, but it's not both.
Well, and also I think the other thing too is, the idea of the engine too. Like I'm thinking they're all combustion engines. They're all using gas.
Yep. And now you throw in
EVs,
EV.
and like now my model's ruined.
Yeah. So the car one's good because you start with this beautiful, like, I have a parent called vehicle, and then I have all my children. They're all siblings. Truck, car, van, motorcycle.
Mm-hmm.
And then we throw in and then
It's a very small parent child sibling tree structure.
it's very shallow.
It's very easy to understand.
Yeah. Then you get into the crossover, and now you're like, okay, well, it's somewhere.
Can you just define a crossover? Because I'm not as much of a car person.
Yeah, it's like if a car and truck had a baby. Like
okay.
they take elements that they like of a car, they take elements they like of a truck, they make a crossover. Or I'm thinking of like an SUV.
Yeah.
So you had an SUV and you had a car. Crossovers like in the middle of it, and then you had those weird trucks that like started popping around in the 2000s, where it was like a low truck that kind of felt like a car. It had a really shallow bed. Essentially, what car manufacturers started doing was they were like, we don't want to be defined by these categories. We just want to start making different vehicles, pulling things that we like from all the different things that we do. And imagine if you're storing all that stuff in objects in C++ or C#, you start to run into a problem because the parent-child relationship gets really muddled.
Mm-hmm.
You start having to create these intermediary parents that sit between the child and the grandparent that don't really make a lot of sense just to reuse code.
We're talking about inheritance in a very classical sense, as it is a concrete class that has fully implemented functionality. So like in the case of a car, it might have start, stop, brake, gas, whatever it is. And then all those things do the same thing. It's going to say like engine dot torque up or torque down or brake or whatever it is. And the vehicle will have that implementation, and everything else inherits from that. And they might have some abstract methods because they might have something different, like how many wheels they have to turn or something like that.
Yeah.
We're talking about that that idea of an inheritance. So
What I think happens, and I know you see this, is when you start to go down this inheritance path and you start to realize that there is no common definition of how something operates, but you know that they do need to do this thing. There's a vehicle, or I shouldn't use that word. There is a method for doing that in traditional inheritance that obfuscates that a little bit. Can you pick up what I'm putting down?
with the abstract methods?
Yeah. So like talk a little bit about abstract methods sort of and how they're typically used.
Yeah, so you got a couple different ways of abstract methods. So you have, if you go back to old C, C++, there's what they've coined it as is you have your pure virtual or non-virtual or virtual, and it's the same idea with abstract. So in things like C# and C++, or in things like C# and Java, you can put something as abstract, and what that's going to say is I'm going to define a signature that you have to implement. When you were in C++, that was something known as a pure virtual method, because you would just put the word virtual at the beginning and you would give it no implementation.
Yep.
Then you have the impure virtual, which has, or in some cases with the abstract as well, because in this case it's still the same keywords. Actually, no, sorry. C# and Java, you have to put the word virtual in front of it to have it be impure, because if you do it abstract, you have to define the whole thing. But you can give it a partial implementation, and then the child can then would call the base and use that same functionality and then add around it.
Onto it, yeah. And all of these things, they solve the problems that generally arise from like traditional inheritance. But as systems grow more complicated and data structures get more sophisticated, and designers don't want to be bound by any sort of limitations, as we kind of alluded to in our vehicle analogy. That style of monolithic architecture slowly starts to break down.
Yep.
And
it gets very difficult to maintain.
yeah, it's now when you're adding new different types, you have to sort of go through the family tree, if you will, and create new layers in this family tree to encapsulate shared functionality, and everybody in the tree is affected by the change.
Yeah, so let's take that, that crossover example. So like first we had the vehicle, and then we had our car and truck. Then we had to add an SUV into it. Well, what's an SUV? Well, it's a cross between a car and a truck.
Yep.
Now we're adding a crossover, which now is another cross between an SUV and a car.
Yep.
So it's, so if you're to even inherit in that way, like you can't have the SUV inherit from the car and it just doesn't make sense.
No,
like the
so
tree gets muddy.
So you end up creating these
intermediaries,
these abstract classes that have no merit in and of themselves, but just contain common functionality.
And yeah, so you got your vehicle, then you have a car-ish.
Yeah.
And then you have a car, and then you got your SUV, and then you're going to have your car-ish too, I guess.
Yeah.
To have the crossover take from the SUV and the car.
So ashamedly, I did something very similar to this a long time ago. I was building a repository pattern for a SaaS product, and there was different types of data. There was data that was going to be global across the platform. There was data that was going to be distinct for every implementation of the product. There was data that was going to be distinct even among each tenant. And there was going to be data that could be testable and data that could be auditable. And I ended up creating this very convoluted lineage of
right, because you needed
classes.
You needed to partition or classify the data in 10 different ways.
10 different ways, yeah. And I got lucky. I was able to have it be a fairly straight path with some branches jotting out. But when it came to running it and debugging it and introducing change and maybe adding a different type of data elements to it,
it was the worst.
It was the worst. It was hard to debug. Things broke. We had to restructure it. So that was like a terrible example of inheritance. But I started looking at the problem in a way where it was, there's common functionality, so there should be a base class.
Yeah, it was. It was looking at it functional versus responsible.
Yeah, I wasn't looking at it as the has a is a model. Like they.
Yeah, for how do you define if it should be inherited or not? You guys know the solid principles. That's where your L for your Liskov substitution. If it walks like a duck, quacks like a duck, then it is a duck.
Yeah.
So that's where the inheritance comes in from there.
Yeah, so like that was an example, kind of like our vehicle one, where I wanted there to be common functionality, but I sort of looked at inheritance as this hammer, and I was like, yeah, we're just gonna make this work. And at the onset, it was fine because I think there were only one or two different forms of this, and then as the product grew more complicated, I started realizing there's elements of this data access and retrieval and saving that are common among these different types, and it turned into a nightmare. So then you have composition, which is essentially a counter to inheritance, and composition is essentially what it sounds like. It's instead of an is-a relationship, it's a has-a relationship.
The way I always conceptualize it, well, not always, but sometimes is like bubble tea with all the tapioca balls at the bottom. Like each of those are your little composite objects.
Oh yeah,
that makes up your
that's a really
little
good
smoothie thing.
That's a really good analogy for that. That's a composite.
Yeah, it's a composite drink. Yeah. Composition helps you with like the limiting the role of what this class is going to do.
Yeah, the class doesn't have to care about who its parent is or what its children are going to be. It just cares about the things it needs to do.
Yeah. And it really starts becoming a little bit more functional to some degree rather than like, so in the case of, I think the example that, we've been talking about off air has been about images. The example is, like I need to give you an image, or I need to load an image or save an image. Like it doesn't matter what kind of image I want. It could be, a BMP, it can be a PNG, it can be a JPEG. Heck, it can even be a GIF. It doesn't matter, right? It's going to have a load and a save, and they're all different data types, and they're all going to have different ways of doing things. And if you were to build a system, like a file system or something, like, hey, find all the files find all the images on my computer and load it, boom, done. And the system is completely unaware of what it is, how it needs to do it. It just knows I have a type of image and I'm going to do my business.
Yeah. So, and there's a really helpful video that we'll have a link to in the comments, but it talks about this analogy of trying to use inheritance to define an image versus composition, where if you have an image base class and then you have a JPEG, a PNG, and a GIF, and they all share functionality for loading and saving, among other things, right? And then you're asked to create a new type of image that there is no underlying file. You're just drawing, basically. It's no longer an image. It's according to the definition of the base class. So in the example they're describing there, what you would have to do in the case of inheritance is you would have to take out the load and save functions, move them into something else, and then it's image, and then there's another intermediate class called read writable image, maybe readable image, or writable image.
Yeah, there's a file. Yeah,
read writable. It's a nightmare. Yeah. And then you'd have your JPEG, which would inherit from whichever one makes sense, and then you'd have your drawable image, which would just inherit straight from the base class. In composition, instead of PNG being an image, PNG has an image, and then it also has a methods for reading and writing. And the way that it defines the has-a is interfaces. So imagine a class called PNG that implements iImage, and then it also implements iReadable, iWritable. So it implements 3 different interfaces. Yeah. The composition here is you have PNG that has an image. It has another interface to do the reading. It has another interface to do the writing, and then the PNG class uses those interfaces to do all of their things. And we use this pattern all the time when we're designing APIs. We say this API has a dependency of this service, of these 3 services, and these services have dependencies of these repositories and these other things, and we no longer pass around concretes. We no longer associate things by concretes. Everything is done using these interfaces. Yeah, that is the composite pattern. And the image one is a great analogy because you would think that a PNG is an image, and a GIF is an image. But even in the is a scenario, they're still advocating for has-a.
Yeah.
So, and it's the is a relationship should be done very deliberately. And I know you can think of an example where we've done this well in the past.
Yeah, I think one of the examples that we've talked about off air here was ironically another repository pattern that we've discussed. And what we've done is instead of making a bunch of different implementation or different sub breakdowns of what it may be, there was just a basic repository that essentially handled all of our CRUD operations.
It's a generic repository.
So very generic.
Yeah. You'd pass in a type and then it would have read-write methods for all those types.
Yeah, because it's interacting with tables, and it's going to do what it's going to do, and it's going to do it good. If you needed to change the data interface, sure, then it might be a SQL connection versus whatever, but it's give it your data type, it's going to give you all the CRUD. And then if you needed something more special, then you would make a new interface, and it's going to do those specialized procedures. Whether that you write that in LINQ or whether that you write that in SQL, doesn't really matter. Who cares? But it's well defined and what it's going to do. So if you need to, again, do it for a different data source, you can do that, and it's not going to matter.
Yeah, and with the database being sort of the central bus to data, we wanted us to essentially centralize all
point of failure in like
to
one
spot.
area.
Yeah.
But it was a very, very deliberate action. And I know we talked about this one before I even wrote a line to code is what's the expectation of engine change? Are we going to change it? What are we going to change it to? Oh, we're just going to update the version. Okay, so like we're going to build it in this way. We're not going to switch from a SQL database to a NoSQL database.
Yeah,
which could very well be an option for some people, but
this argument for, and I'm just going to reiterate this argument for compositional over inheritance, it's not saying that inheritance is bad. What it's saying is that there's risks associated with it, and there should be consideration beyond the is a has a question. Because as we've sort of described here, there are times when something is a something, and even then change will come that will challenge that sort of structure.
Yeah. And honestly, like, and even if one of the things, and this is a very challenging thing, I think, with interfaces on a regular basis. If you have everything that's in it, is everything going to be used 100% of the time?
Yeah, it's the
like 99 isn't good enough, right? It has to be, because there's been so many times that I've worked on products that have been like, there's a base component. Well, they just have all these helper interfaces because, well, I don't want to redefine it.
Yep.
Sure, but like at that point, now you're just adding cruft. And I should say this isn't front-end frameworks too. This isn't back-end. Back-end, at least it'll optimize some of that out.
There's a name
front-end, it's not going to.
There's a name for that. For that problem, or it's the
garbage method.
Well, the gorilla banana method or problem. I forget how it's framed, but it's the idea is like I need a banana, but I have to. The only way I can get the banana is by taking the gorilla, because you've sort of attached the banana to the gorilla. Like,
oh man.
So it's like again, another argument for composition is it allows your code to.
So you can get more bananas.
Yeah, you get more bananas. No, you can create things a lot easier without all of the unnecessary baggage that comes with high levels of inheritance.
Yeah.